So we are going to perform LCR series and parallel circuit experiment in which our aim is to study the frequency response and to find resonant frequency of LCR series and parallel circuit, also to find the quality factor and bandwidth in LCR series circuit. The apparatus required is a variable non-inductive resistor, a variable capacitor, a variable inductor, a signal generator, an AC milliammeter, and the connecting wires. The formula used here is for resonance frequency is 1 upon 2 pi root over LC, which gives answer in the hertz, where L is self-inductance and C is the capacity of the capacitor, basically capacitance of the capacitor, which is in microfarad. Next we will calculate bandwidth, which is given by F2 minus F1, which is in hertz, and also the quality factor is equal to F0 upon F2 minus F1, where F1 and F2 are the frequencies at the half power points. This experiment we will use our kit. Our kit consists of resistor. There are three resistor given here, one inductor, three capacitor, but we will use three of these resistor, one of the inductor and one of the capacitor. Also here milliammeter is given, which we will use to measure the current.
This is our power supply, which is also called as function generator, through which we will give desired frequencies to the circuit. We will keep frequency range in 10K as our frequencies are given in kilohertz. This is the circuit diagram in which the positive terminal goes in the resistor, then after it goes in the capacitor, then after it goes in inductor, then it is connected to the milliammeter, and then it is again connected to the negative terminal. According to this circuit, we have connected the connection. The positive terminal of power supply goes in the resistor, then resistor goes to the capacitor, then capacitor is connected to inductor, and inductor is connected to the milliammeter, where we will measure the current, and then milliammeter is connected to the negative end of power supply. Now we are going to perform the experiment. This is the observation table where frequencies are given in kilohertz. We will measure the current through resistor 47 ohm for these given frequencies and note it down. Now we will begin the experiment. We will keep frequency range up to 10K. Through this knob we will adjust our frequencies. The first one is 0.85 kilohertz. For this frequency, now we will note the current. The current is in milliampere. The least count is 1 milliampere. So we can see here for frequency 0.86, the current is 3 milliampere. So we will note it down. Now we will note current for 1.12 frequency. We will adjust frequency with this knob. We can see here it is 4 milliampere. Now we will note it down. Now we will note values of current for these given frequencies, and we will follow the same procedure for two more resistors, that is 100 ohms and 150 ohms.
So we have noted the values of the current obtained for various frequencies. For the frequency that is 3.07, we have received the current 22, and which is the maximum value of current in all three resistances. So now we will plot the graph, and you can see we have plotted the graph of I versus frequency, which is in kilohertz, and for this R units fixed as in x-axis 1 unit represents 0.25 kilohertz, and in y-axis 1 unit represents 2 milliampere. We will do is calculate 70% of 22, which is actually VRMS, or we can say RMS value. So for calculating VRMS, we will do 70% of 22, that is 70 upon 100 into 22, which will give the result 15.4. We will see that point in our graph, that is 15.4 milliampere, and draw parallel line to our x-axis, and we will see 2 points where this point matches our graph. Basically, we have plotted here three graphs, but we can plot them individually or we can plot them into the same graph paper. That depends on us. But for the first graph, we can clearly see that our RMS value of current is touching our graph, our first graph, at two positions, that is F1 and F2. So we will draw a parallel line to our y-axis. So now we will use that point F1 and F2 to calculate our bandwidth, which is basically equal to F2 minus F1. One more important thing to note from our graph is the point at which we are getting the maximum value of current, and if we see the frequency responding to that point is the resonant frequency, and here it is 3 kilohertz. So next we performed our calculation for 47 ohm, that is the calculation part A, and for this first of all we have calculated the bandwidth, for which we have used our frequency F1 and F2, and bandwidth is basically equal to F2 minus F1, so we did here and we got the result 1.58 kilohertz. And now we will use our from our graph we have got resonant frequency, that is F0 is equal to 3 kilohertz. And now next we will calculate the quality factor, and the quality factor is basically equal to F0 upon F2 minus F1, and so we can clearly see here that the value is 3 upon 1.58 and we have got 1.898, and quality factor is obviously free of units, that is it is unitless. Then we have calculated our F0, that is resonant frequency, by the formula 1 upon 2 pi root LC. Then we have substituted the value. We can clearly see that L is in 30 millihenry and our capacitor is of 0.1 microfarad. By using the calculator we have calculated this value and we have obtained the result approximately 2.9 kilohertz. Now we will see the result. So in the result we have obtained the frequency F0 by the graph is 3 kilohertz, the F0 resonant frequency by calculation, that is 2.9 kilohertz, quality factor that is 1.898, and bandwidth that is equal to 1.58 kilohertz. So with this we conclude our experiment. But obviously this experiment can be repeated with the other given two resistors, that is 100 and 150 ohm.
Now we will briefly explain the theory behind the LCR circuit experiment. An LCR circuit is an electrical circuit that contains three main components: a resistor, an inductor and a capacitor connect to alternating current supply. First, let us understand these components. A resistor is a component that opposes the flow of electric current. It converts electrical energy into heat and its unit is the ohms. An inductor is a usually coil of wire that stores energy in the form of magnetic field. It also opposes any sudden change in current flowing through the circuit. This property is known as a self-inductance and its unit is the Henry. A capacitor is a device that stores electrical energy in the form of electrical field. It consists of two metal plates separated by an insulating material. The ability of capacitor to store charge is called a capacitance and its unit is the farad. In the experiment, these three components are connected to form an LCR circuit which can be arranged either in series or parallel. In series circuit, the resistor, inductor and capacitor are connected one after another. So the same current flows through all the components. In parallel circuit, the components are connected side by side, so the voltage across each component is the same, while the current divides into different branches. Another important concept in this experiment is frequency. Frequency is defined as the number of cycles per second of an alternating current and it is measured in hertz. The most important phenomenon studied in the experiment is a resonance. Resonance occurs when the inductive reactance of the inductor becomes equal to the capacitive reactance of the capacitor. In other words, when the effects of the inductor and capacitor cancel each other, at this condition the circuit responds strongly to that particular frequency. In an LCR series circuit, the impedance becomes minimum and the current becomes maximum at resonance. In an LCR parallel circuit, the impedance becomes maximum and the current drawn from the source becomes minimum. The frequency at which resonance occurs is called the resonant frequency and it's given by the formula Fn equals 1 divided by 2 pi square root of LC. In this experiment, we also study the frequency response of the circuit. This means observing how the current changes and the frequency of the AC supplies varying by changing the frequency.